Section 3 is all about functions, and you might have met these before, but I'm going to try and give a nice large definition of what a function is, so that later we can start talking about properties that functions might or might not have. But first I need to show you a definition and some examples so that we've got some functions to work with. Okay, here's my definition of a function. Say you've got sets x and y, then a function from x to y is a subset of the Cartesian product between x and y. So pairs of values in the Cartesian product, remember, that's pairs of values, thing from x, comma, thing from y, wrapped in round brackets. But there's a property, it's not just any subset of the Cartesian product. The property is that for each x in the set x, there's exactly one value of y such that the pair x comma y is in the subset. And this is exactly one in my definition, so one and only one. This is probably not what you had in mind when you were thinking about functions at the start of this video. This is probably not what you work with when you're working with functions in general, and in fact some people would say that what I've defined is actually the graph of the function, the thing that you draw. But for me, the function is defined as a subset of that Cartesian product with this property. Of course, probably the thing that you think about is more of a map or a mapping or a motion from x to y. Things start in x and get moved to values in y in some sense. Maybe you write things like this. For each x in x, there is a particular element, an assignment, f of x, which is an element of y. So one and only one value that's associated with x. So for each value of x in the set x, you have some chosen value in the set y. The reason I haven't put it like that in my definition is that I think that makes it sound like you need a particular rule in mind. You need some sort of organised plan. And all I really need is that you have exactly one value of y. I don't mind if your rule is squaring or if your rule is something more esoteric. I don't really need you to have a written rule at all, so long as we're sure that there's exactly one value of y for each value of x. Property of a subset, really, for me. Anyway, the thing that we're going to talk about for the rest of this is the assignment of a value x to f of x in y, and we're going to draw diagrams perhaps like this with arrows showing that happening. So for each element x in the set x, we have a value f of x in the set y. For the function, instead of writing from x to y, we might show it like this. So this is the notation for a function from x to y. There's a colon here and an arrow here. The arrow is highlighting that mapping idea from x to y. And these have got names. For a function from x to y, the sets x and y have names. They're called the domain and the codomain. I have a note about codomains later on, but I'm going to call them domain and codomain. So for a function from x to y, we call x the domain and we call y the codomain. So if you're showing a function, you have to be told what the domain and codomain are, but then if you want to refer to them later, you can call them domain and codomain for that function, instead of clumsily saying x and y like I've been saying so far in this video. So here I might say that the function takes values in the domain and returns functions in the codomain. For each value in the domain, there is a value in the codomain associated through the function f. Okay, we should probably look at some examples, but first let's note that functions are only considered equal if they have the same values, but also the same domain and the same codomain. So this is a fine distinction, a narrow distinction, but functions are only considered the same if x and y, if you like, are the same for these two functions. We're going to see some examples of very similar looking functions where the domain and codomain are not the same. And if that seems pedantic, I'm afraid it's necessary if we're going to talk about properties that the functions have, because those properties might depend on what the domain is or what the codomain is. So if we're sloppy on which particular version of a function we're talking about with different domains and codomains, then it might or might not have these properties. You've got to be precise about these things if you want to talk about properties of the function itself. Okay, obviously you want the same values for every x in X. I can't remember if I said that out loud or not, but you definitely want to agree on the values as well. That is important too. Okay, examples. So the ceiling function, you could define this as a function from real numbers to integers that does some rounding up. It returns the least integer that is greater than or equal to x. So that's a bit to think about there. The least integer that is greater than or equal to x. I've got an example where it might be equal to. -4 is the least number that is equal to or greater than -4. But for non-integers, it does the rounding up sort of thing that you're expecting. F of 3.1 is 4, f of pi is 4, f of 3.5 is 4, f of 4 is 4, but then f of 4.001 is 5. So this is defined, but for example, and then I put a complex number in here, that's not defined because this number here is not in the domain of our function. Now, of course, you could invent some way, if you like, of rounding up complex numbers. You're welcome to go and do that, but your version will be a different function. Probably you'll agree on how to round up real numbers to do the same thing as this function, but just by extending it to also have some made-up definition of how to round up complex numbers, you're now talking about a different function with a different domain. We'll see other examples in a second, but let's note that you could define a function that does something similar but takes real numbers and returns real numbers just by doing exactly the same calculation, because of course the things it's returning are real numbers. 4 and -4 here, they're real numbers. They happen to be integers, but they're also real numbers. That function would also be considered different because it has a different codomain. In this case, the codomain is z, the integers. In the one I was just considering, it would be the reals. And even though all the values are the same for everything in the domain, it's considered a different function. We'll see why that matters when we get to some properties in the next subsection. Okay, I've got another example, and I want to show you some notation as well. When people are showing what happens to a particular element of the domain, you sometimes see this arrow with a little vertical line on the left like that. So x maps to f of x is how you read that. So I've got an example of that. I want you to notice that I'm describing the function from naturals to naturals with n maps to n plus 1. So I'm being pedantic here, I know, but it's this shape of arrow for the explanation of what the domain and the codomain are, and it's this sort of arrow for what's happening to the elements inside the domain and the codomain. This is important, I think, because the function f is not the same thing as the value f of x. People do get them mixed up sometimes when they're writing. I know I've got them mixed up before while writing, but I'd like you to try not to get them mixed up. That f is the function. If you like, it's a subset of a Cartesian product. It's a strange thing. But f of x, that's just some number in the set y. Assuming y is a set of numbers. It's something in the set y. It depends on x, but it's not itself something strange and exotic. When we're talking about properties of a function later on, they might involve the values of the function, but we're going to be talking about properties of f and not properties of f of x. In the previous example, f of x was an integer, but f is not an integer. F is a function. Okay, right. So we're not going to mix up f and f of x. And we're going to try and remember to use different styles of arrow because that's what people do. That's the notation that's out there. Sometimes you might try and come up with a recipe and it doesn't work. The rule is for every element of the domain, you need to have an assigned value of the codomain. So here's an example. X maps to 1 over x. This is not okay because 0 maps to, well, I don't know, there isn't a real number that's 1 divided by 0. This assignment just fails. We could fix that by deciding what 0 maps to, not 1 over 0. We need to pick a real number, but we could choose whatever we like and then it would be fixed. So the assignment that's defined piecemeal by x goes to 1 over x if x is not 0, and x goes to 3 if x is 0, then that's fine. That would make it a function. Not my favourite function, I suppose, but for every value of the domain, I've now successfully defined a value of the codomain. Similarly, the recipe f of x equals y, where y squared is equal to x. So in this example, I'm using the f of x notation that you might have used before. This fails for 2 reasons. One is that if x is negative, then I've got problems, assuming that I'm still talking about a function from real numbers to real numbers. And the other more subtle problem is that when x is positive, this recipe doesn't tell me whether I should use a positive or negative value of y. So does f of 4 equal 2 or minus 2? This could be fixed if we were talking about a different domain and codomain. Notice that's important. When I say for every x in the domain, implicitly that relies on me knowing what the domain is and worrying about all of these things in the domain. So we could fix this function by being more restrictive about the domain and codomain. Okay, in cases where it doesn't work, we might say that the function is ill-defined. And I've said with VV twice, but I want to cross it out anyway because I'm not sure I would say it's a function. It's ill-defined and ill-typed. We're interested in the opposite, functions that are well-defined, which is the phrase for a function that obeys the definition of a function, which is all of them. So that's sort of a tautology, but you do need to check. Yes, every well-defined function satisfies the definition of a function. Every function satisfies the definition of a function. It's the same idea, but highlighting the need to actually follow all of the rules in the definition. There you go. There's a subtlety sometimes when you're looking at functions where numbers have different representations. So we mentioned before that in the rationals, you have different ways to write the same number. And watch out for that because you need to make sure that for each number, you have a unique element in the codomain. So this plan, that give me a rational number m over n, and I'll give you return n, then this is not good because, well, 2/3 and 4/6 are supposed to be the same number in the rationals, so they should return the same output in the codomain. And that's working with, obviously, a definition of the rationals where we consider 2/3 and 4/6 to be the same thing. We could fix this, well, we could fix this by tightening up our definition of the function to talk about particular representation of each number in the rationals. You might insist when you set up the rationals in the first place that the numbers are coprime, that they have no prime factors in common, m and n. Or we could fix it in the function by saying, okay, you might show me m over n where they have some common factor, but my function should allow for that by converting the fraction down to something where I suppose it's n divided by the highest common factor of m and n. So we could sort of fix this later on by either adapting the set of numbers that we're looking at, or the set of representations of numbers we're looking at, whatever, or by changing the function to make sure that we have, either way, for each thing in the domain, whatever that is, you have a unique assignment in the codomain. Okay, so there are some examples of things to watch out for, and especially it's around if your domain has multiple ways to represent the same number, then you've got to be careful with that. Okay, so I've got 4 functions on the screen here, and all of them do the same thing to the number 3. They all agree that if the input is 3, then the output should be 9, but they're all different functions because they have different domains or codomains or both. So in some cases I'm talking about the unbounded interval that includes 0 and all positive numbers, and in some cases I'm talking about all real numbers. So remember, this notation with the square bracket includes 0, and with this infinity on the end means that it's unbounded, so it's everything that's greater than or equal to 0. I have to include 0, of course, when I set up this function f2, because my plan is to send the number 0 to 0. So I need to make sure that's in the codomain so that this rule works. And you might like to quickly check that in each case it really is true that for every number in the domain, let's just highlight the domains, so the domain here, 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 and here, for each number in the domain, you really do get something in the codomain in each case when you do this squaring calculation. Quick pause to think about that. Yes, real numbers always square to real numbers always square to positive numbers always square to real numbers, positive numbers always square to positive numbers. Goodness me. Right, so that's some examples of some functions. We're going to now define quite a lot of things to do with functions, looking at the image of a particular number. We were just talking about what happens to 3. We're also going to try and talk about the image of a set. I've got several warnings for these, so I'll show you my definitions and then explain the warnings afterwards. So here we are. So the image or range of f, some function from x to y, is the set of all points in y given by f of x for some x in the set x. So the idea here is that you take everything in the domain, you apply f to each one of those objects, you will return some huge group of things in the codomain, and I'm interested in which ones you get. So the idea is applying f to absolutely everything in the domain and just seeing what you get. This has to be a subset of the codomain because the rule for a function is that whenever you apply f to an element of the domain, you always get something in the codomain. So everything in that set that I'm talking about belongs somewhere in the codomain. So that's the image or range of a function. More generally, we can think about the image of a subset of the domain. So if you're interested in just part of the domain, some subset A, then, well, the notation for this is f of A, and the idea is that you apply f to all of the values in A and put them together in a set. So this set over here is defined as f of x such that x is an element of A. And once again, when you apply f to things, you're getting values in the codomain, so this collection of things is a subset of the codomain. It's a subset of the codomain again. We can also try to go the other way. So the sort of natural question here is, given a subset of the codomain, what can we say about the domain relative to that subset of the codomain? And the best we can do at the moment is to talk about the pre-image of B under the function f. So the pre-image of B, that's defined as all of the points in the domain that get mapped into B. So I want any values x that you can find such that when you apply f, you get something in B. There's a couple of subtleties here. I'm being really careful to say pre-image and not inverse function. We haven't got to inverse functions yet, and this might or might not be an inverse function. There might be no such thing for your function f. We'll see that later on. Saying pre-image, the idea being that these things have, the best I can say is that when you apply the function to them, you will get something in B. I'm not claiming you get everything in B, and I'm not making any other claims really at all. Maybe there are other things that you might think I'm claiming, but goodness me, I'm really just saying this is the set of everything such that when you apply f, you get something in B. So it's a subset of the domain. It's the best I can do is points of the domain that map in there. So I'm being quite apologetic here. Let's see why. I have 3 warnings. Some authors say range for what I would call the codomain. So for a function that takes some of the values in the codomain and not all of them, then we would disagree, because I would say that the range of f, in that case, where it doesn't take all of the values in the codomain, I would say the range of f is different from the codomain, and other authors might be using the word range for codomain, and they may have a different word for range. They might say image. So for some authors, image and range are different. For me, range and codomain are different. Second warning, the notation there is f applied to a whole set, and the definition is that means that you apply f to each of the elements and build a set out of what you get. That is not obvious behaviour. It needs a definition. Formally, f was only defined in the first place, of course, for elements of the domain. So f of x is the thing I was expecting to write, of course. Whenever I look at a function, I have some x in x, and I have f of x, and that's an element of y. But we have this other notation that gets used quite a lot to say, I want to apply f to everything in this set, where we're expected to do a bit of unpacking, applying f to everything, and then repackaging it back into a set. Let's point at that again. So over here, take all of the values in A, apply f to each of them, and repackage that as a set, talking about a subset of y. This always works, but I want to be really clear that it's different from applying f to a single element of the domain, and it needs a separate definition. So I'm going to try and be really careful and say pre-image of B every time I see this, and not f inverse of B. Again, we haven't defined inverse functions yet, and the pre-image is defined even if there isn't an inverse function. So even if we never get to having an inverse function, we have this idea of the pre-image, the points of the domain that at least they map into this set B. So even if you don't have an inverse function, you might have something like this. Note again that it's doing a thing where it's applied to a whole set of elements in the codomain this time. So we're again expected to do a bit of unpacking, to look at each element in B and see if we can find any elements in the domain that map to that element of B. Once again, looking back at the definitions. So you're looking for any possible f of x in B. There might be lots of things in B, and you're expected to find all the x values and package those into a set. So remember, this notation is it's a set of values of x such that some property holds. So again, we're supposed to do that sort of unpacking and repacking. Sorry for all the warnings. I just want to be really clear with the warnings up front in a course like this, so that later when they turn up in your mathematics, you've been warned. you know that sometimes the function is being given values and sometimes sets, and we've all just agreed that that's okay. They're both defined, a sort of double purpose f that works on elements and works on sets. Something we're up to. Okay, so thinking about those functions again with the different domains and codomains, they've got different images and different preimages of various sets because they have different domains and codomains. So we're going to work through a couple of them. Think about that first function where the domain and codomain were both real numbers. Then the image, which means, reminder, for the image we take every element of the domain, we apply the function to it, and we make a set of what we've got. So here if I take the values, well, I put in any real number I can think of, then I'll get the numbers from 0 and upwards. I won't see any negative numbers, but I will see everything else. So the image is precisely this unbounded interval. And here's an example thinking about the image of a set. So here I've got square brackets for the closed bounded interval, numbers between 0 and 1 inclusive. And if I square those numbers, well, I get numbers from 0 to 1 inclusive, because 0 squared is 0 and 1 squared is 1, and I get everything in between. And so the image of that interval is this same interval. The preimage of that interval, though, includes some negative numbers, because the preimage of that interval looks at all possible numbers in the domain that map to things in this set. So this is the one where the definition said f to the minus 1 of b, the preimage of b, and that includes loads of other things. Our function, in this case at the top, sends positive and negative numbers to the same values, and that's been sort of detected here. We took some the function applied to some interval goes this, but then the preimage of that interval includes some other stuff. The preimage of this interval, negative numbers or 0, so square bracket means we're including 0, the preimage of that is just the set containing 0, because out of all of the negative numbers, nothing squares to any of them, and like 0 is there as well, and 0 squares to 0. It's the only thing that squares to 0. I have tried to do this properly and write down curly braces around the 0, even though I don't love this notation. We're doing the preimage of a set, we should return a set. So even though it's a set containing one number, I'm still writing it as a set. My preimages are always, the preimage of a set for me is always a set. Here's another function. So we also looked at something called f4 earlier, which just looked at the non-negative numbers. Again, doing some squaring. So the image is, again, that interval. I've got rid of negative numbers, but they weren't really changing the image, it turns out. And if I take the image of this interval, well, that's the same interval I had up here, and when you square those numbers, you still get numbers from 0 to 1 inclusive. But now when I take the preimage of this interval, I now just get the interval from 0 to 1 inclusive, because I don't have any negative numbers in my domain anymore. So maybe you can see this question of, does the preimage of the image get you back to the set you started with? That depends on the domain and the codomain. It's not just a question about squaring, it's also a question about the domain and the codomain, because your domain could include other values that are doing other things. The preimage in this case of this interval is not defined. It's not 0, it's not the set containing 0, it's not the empty set, it's not the set containing the empty set, it's just not defined. And it's not defined because this set, which we could call B, is not a subset of the codomain in this case, because our codomain doesn't include any negative numbers anymore. So it's just not defined. the preimage of a subset of the codomain requires you to have a subset of the codomain. Okay, so things are going swimmingly. We have a function that we can apply to numbers, or by convention we can apply it to a whole set of numbers in our domain. And we can talk about preimages, but maybe we're feeling a bit nervous about whether the preimage gets us back again or not. So that's a good sort of nervous, because it's foreshadowing for a definition later on where we'll start talking about inverse functions. I want to show you where we're at, the kind of status quo of where we've got to, through this proposition. In general, for functions from x to y, you might take the image of a set and then calculate the preimage of that, in which case I claim that you get back to a set that contains the things you started with, but it's not necessarily the same set. And the other way around, if you start with a subset of the codomain, you calculate the preimage and then you apply f to all of them, then you'll get back a subset of the things you first started with. The problem there is that when you calculate the preimage, some of the points in C might have no preimage, they might have no points in the domain such that f of x is in C, and then the plan is here to apply f to all of the points that we just found, and it might not be the case that we get back to everything in C. We might have lost some of the points in C. Up here the problem is, well, we just saw an example of this, didn't we? That the preimage thing finds all the points in your domain that map to things in that set. So, okay, you started with some set A, carefully chosen, you applied f to it, and you got some points in the codomain, but then when you did the preimage, well, you might have found other stuff as well that was also getting sent there. The preimage finds lots of stuff. Okay, so preimage finds lots of stuff for each point in the set B, finds lots of stuff for each point in the set B, but if there isn't anything, it doesn't have to find anything if there's no such point in the domain. So I've got a proof of each part of this. The proof looks more complicated than it really is, because actually both of these make sense if you just chase through what the definitions are, and I want to focus on showing you counterexamples for these demonstrations that we don't have equality in general. So in part A, by definition, just following through what these things mean, the elements of A map into f of A, so then the preimage will surely include all the points in A, but other stuff can also map into f of A. So if we consider the map x squared from R to R, and we set the set A to just the set that contains 1, then following it through, this is a smaller version of the example we had before. When you apply f to that set, you just get 1 in curly braces, because I squared 1 and I put curly braces around it because that's how you do a function of a set. And then the preimage of that finds a second number, because the preimage has found that -1 also squares to 1. So it's returned me this set with 2 elements, which is not the set that I started with. And in the second case, where I'm doing things in this order, there might be points in C that have no preimage in the domain. So in general, the whole point of the preimage is that when you apply f to them, you get back to points in C, but we might be missing things. So for this squaring function from reals to reals, if we look at the set that contains -1, well, the preimage of that is just the empty set. There isn't any number that squares to -1, so I return the empty set. And then when you apply the function to the empty set, well, I suppose the rule is, how do you calculate f of the empty set? Well, you take all of the elements in the empty set, you apply f to all of them. There aren't any. You apply f to all of them, and then when you're done, you package those up as a set. So I start with nothing, I apply f to it, I have nothing, I get the empty set at the end, which is not the set that I started with. I had this nice set containing -1, and now it's gone. So in general, you have the problem that things might not have a pre-image. The pre-image thing here is not a function, because there are numbers, possibly, in this example anyway, there are numbers in the codomain that don't have an associated value of x such that f of x is equal to that number, and much less a unique value of x. That's too much to ask for. So it's not a function going the other way in sort of two different ways. Right, okay, that is my proof of where we've got to with the interaction between functions and pre-image. I have a couple of quick definitions at the end here. Given a function and a subset, we can talk about the restriction of f to the set A, which is written like this with a vertical line and a subscript A. In handwriting, I might put it further down like that or something, which is a function from A to Y, defined by just taking the values that you were going to take anyway on that subset. I mean, these values are in A, so they're in X, so I know what to do with them. Importantly, that's considered a different function because it has a different domain. I mean, it's doing all the same things. It's returning numbers in the same codomain, but it's considered a different function. That's called the restriction of a function. And one last important function is the identity function, written id subscript x, id for identity. And that's a function from a set to itself, which is defined in quite a boring way by just taking your value x and returning x. So you can do this on any set x, and sometimes if it's obvious what the set is, people don't write it and just write id for identity. Sometimes people write one subscript x, but I feel a bit uneasy whenever I see a number with a subscript. It feels to me like something's definitely gone wrong, but that is something that people write sometimes. So that's the identity function. I just thought I'd throw in two definitions at the end of functions that you can build quite generally. Okay, next time we're going to learn about some properties of functions, and we're going to start calculating some inverses. I'll see you in the next video.